Hello and welcome. My name is John Morrow. I am a professor of material science and engineering at Penn State University. Specifically, I am a glass scientist. I study glass for a living, and one of the most frequent questions I get as a glass scientist is about the famous stained glass windows in various cathedrals and whether that stained glass is flowing very slowly over time. And so what we decided to do is to test that out in detail to see, does cathedral glass flow? And this is work that was done together with three of my colleagues from Corning Incorporated, Oscar Gulbatin, Xiaochu Guo, and Olish Boritov. And I would like to start this lecture with these beautiful stained glass windows at Sainte-Chapelle. This is a chapel that was built by King Louis IX, better known as Saint Louis, of France. This was back in the mid 13th century. Sainte-Chapelle is just outside of Notre Dame Cathedral in the heart of Paris. And this was designed and built by King Louis IX to house the crown of thorns that Christ wore during his crucifixion and also a shard of his cross. And he wanted to design this building to capture the beauty, sort of worthy of being able to store and house these relics. And glass was chosen as the medium for this because of all the different shapes that it could take on, the different colors, also because of its high mechanical strength, its optical transparency, its ability to withstand the elements like water without dissolving or degrading over time. So glass was chosen both for its artistic qualities as well as its engineering qualities. And if you go inside of Sainte-Chapelle, and please do if you ever go to Paris, this is like being inside a beautiful work of art because if you look around, all around you are these very tall, intricate, beautiful stained glass windows. And if you zoom in on any of these, they are showing scenes from the Old Testament, from the New Testament, and scenes throughout history after biblical times, showing kind of a history of the world up through the mid 13th century. And they were able to show this really beautifully using glass as the medium. Now, the reason I bring it up for this lecture is that if you look really closely at any of the individual pieces of stained glass in these windows, you might notice that some of the glass panes are a little bit thicker at the bottom than they are at the top. And this observation has led many people to believe that the glass is flowing over time. If they assume that the thickness was uniform when the glass was first installed, then over time, the assumption is that the glass is very slowly flowing, gradually becoming thinner at the top and thicker at the bottom. Now, this was a problem that was first addressed by my good friend, Professor Edgar Zanotto. He is a professor at the Federal University of Sao Carlos in Brazil. And he believed that this was just kind of a local urban legend in Brazil and was surprised to discover that as he spoke with his colleagues around the world, a lot of people throughout the Americas and throughout Europe did believe or did have this question in their mind about whether cathedral glasses actually flowed. And so he did a study that was published in the American Journal of Physics back in 1998 called Do Cathedral Glasses Flow? And the abstract is shown here. He says, a general belief among members of the scientific community is that glass articles can be bent irreversible and that they flow at ambient temperature. This myth is mostly based on widespread stories that stained glass windows of medieval cathedrals are thicker in the lower parts. In this paper, he estimates the time periods required for glass to flow and to form at ordinary temperatures using calculated viscosity curves for several modern and ancient glass compositions. The conclusion is that window glasses may flow at ambient temperature only over incredibly long times, which exceed the limits of human history. So what Professor Zanotto did was he considered several different types of glasses, and the key property that we need to evaluate whether a glass is flowing or not is the viscosity. And the main equation that was used at that time for measuring or for estimating the temperature dependence of viscosity was this Vogel-Fulcher-Tamman equation, or VFT equation. This was actually proposed empirically way back in the 1920s, and it relates the shear viscosity of actually a glass-forming liquid, and this viscosity is given by the parameter here, eta, to the temperature T, where there are three fitting parameters that are A, B, and T0. And he used this equation considering several different glass compositions, then to extrapolate this viscosity down to room temperature, because the viscosity at room temperature is much too high to measure directly. And so this can only be done by measuring viscosity at higher temperatures and then extrapolating down to room temperature. But based on that extrapolation with this VFT equation, Professor Zanotto concluded that glass could only really flow on a very long time scale, on the order of 10 to the 33 years. So not just longer than all of human history, but longer than the history of the universe itself. So his conclusion is that this is just a myth and that glass was not actually flowing at ambient temperatures. Now, this paper generated a lot of attention. One of the readers who considered this very carefully was another good friend of mine, Professor Prabhat Gupta from the Ohio State University. And one of the things that Professor Gupta noted is that that VFT equation, which shows this is the log of the viscosity versus inverse temperature, this really only captures the viscosity of the supercooled liquid state. And what actually happens is that as the supercooled liquid is cooled through what's called the glass transition range, which occurs at a viscosity of about 10 to the 12 Pascal seconds, it's no longer a supercooled liquid. And what happens is that the structure of that supercooled liquid gradually freezes into this solid-like glassy state. And when that happens, the viscosity curve no longer follows this equilibrium curve predicted by the VFT equation, but rather it departs from that and it freezes in to give this straight line here on this logarithmic plot. This is what's called an Arrhenius plot here that shows a straight line of the log of the viscosity versus the inverse temperature. And this is what he called the isostructural viscosity. Isostructural meaning that it is the frozen in structure. So when the structure becomes frozen in, the activation barrier for the viscous flow becomes frozen in, and that's what gives the straight line behavior here. And so together, Professors Zanotto and Gupta wrote another paper to follow up from Professor Zanotto's previous paper. This was also published in the American Journal of Physics. This was in 1999. Do cathedral glasses flow? Additional remarks. And they used data from a modern soda-lime silicate glass. This is like a modern window glass. Because that's where most of the data have been published for isostructural viscosity, which is a lot more difficult to measure compared to equilibrium viscosity. But using this isostructural viscosity data for a modern soda-lime silicate glass, they came up with a new estimate for the time scale of glass flowing. And you can see that the new estimate was on the order of 10 to the 23 years. So many orders of magnitude faster than Professor Zanotto's previous estimate, but still much longer than the age of the universe itself. And so their conclusion remained the same, that the viscosity of glass at room temperature is much too high to actually observe flow on any realistic timescale. But this huge difference, this 9 to 10 orders of magnitude difference in the prediction between the old estimate and the new estimate shows the importance of accounting for the non-equilibrium character of the glassy state. And this points back to some of the inherent features of what makes a glass a glass. We can see that on this volume temperature diagram on the right. What happens to make a glass is that you start off in the liquid state here in the upper right. The liquid state is at high temperatures and high volume. As a liquid cools, if it stays in equilibrium, what happens is that when the liquid cools just below its own melting temperature, it should undergo crystallization. So it should rearrange the atoms in the liquid from their disordered liquid structure into an ordered crystalline configuration. When that happens, the liquid undergoes a first order thermodynamic phase transition. This leads to a discontinuous change in all of its thermodynamic properties, including its volume. And then what you get is a crystal. And a crystal is a solid material. It no longer has a viscosity, so it no longer exhibits viscous flow. Now, that's what happens at equilibrium. Glass is a non-equilibrium material, and in order to get a glass, what we have to do is take this liquid and cool it so fast through this shaded region here where the liquid is likely to crystallize. So we cool it so fast through that crystallization region that the atoms simply don't have enough time to rearrange themselves into a nice crystalline order. And when that happens, you get a phase called the supercooled liquid. A supercooled liquid is any liquid that is cooled below its normal freezing point. From a thermodynamic point of view, this is not the equilibrium phase. The equilibrium would be the crystal. The supercooled liquid is what's called a metastable equilibrium, meaning that if you leave it unperturbed, it would be stable, but it could undergo a phase change to lower the Gibbs free energy of the system and to reach a more stable thermodynamic equilibrium. So the supercooled liquid is stable on its own, but if you were to take this and either wait long enough time or heat it up into this shaded region where it is more likely to crystallize, then it would undergo this first order phase transition and then crystallize. Now, that's a supercooled liquid. How do we get a glass? To get a glass, we take the supercooled liquid and we continue to cool it. As we continue to cool the supercooled liquid, the viscosity is becoming higher and higher, meaning that it is becoming more and more difficult for the supercooled liquid to flow. So you can think of this as going from a really low viscosity like water to a much higher viscosity like honey. And if you continue to cool it, the viscosity becomes higher and higher and higher. Eventually, the viscosity becomes so high that the time scale that is required for flow becomes longer than your observation time scale for actually observing that flow. When that happens, we get a departure from this metastable equilibrium, and this corresponds to a gradual freezing in of the structure of the supercooled liquid. So the supercooled liquid, the structure is gradually becoming frozen in into a solid-like but still disordered state. And that resulting material is what we know and love as a glass. So a glass has some properties that are like a solid because the atomic positions are more or less frozen in. It behaves mechanically a lot like a solid, but it has the structure of a liquid because the structure of the glass is just the disordered structure of the liquid that becomes frozen in. And like a liquid, a glass still has a viscosity. It is a very high viscosity, but it is an intrinsic property of the glass. And if you wait long enough, or if you heat up the glass, you can observe that the glass will, in principle, flow over time. Now, this connection between the glass and the liquid state is called the glass transformation range or the glass transition range. The transition between the supercooled liquid and the glass, it's a gradual freezing in process. And so some of the key features of the glass, because of this glass transformation or glass transition, is that glass has a non-crystalline structure. It doesn't have this well-ordered structure like you get in a crystal. Instead, it has the structure that is much more similar to that of the liquid. Also, glass has fallen out of equilibrium, so it is a non-equilibrium state, which means we can't use the same equilibrium physics to describe the structure and the properties of glass. And because of its really high viscosity, there are long time scales associated with the flow of glass, the so-called relaxation behavior of glass, as it gradually tries to go back to its metastable supercooled liquid state. So these are some of the main challenges of studying glass. These are some of the things that really drew me to become a glass scientist in the first place, because even though this is a very old material, thousands of years old, it is at the cutting edge of materials physics. And it's largely because of these things, because of its non-crystalline structure, its non-equilibrium thermodynamics, and the very long time scales of the viscous flow and other kinetic properties. And in fact, a Nobel Prize winner, Phil Anderson, who won the Nobel Prize in Physics back in 1990, or 1977, published a paper where he said that the deepest and most interesting unsolved problem in solid state theory is probably the theory of the nature of glass and the glass transition. This could be the next breakthrough in the coming decade. So this is really at the cutting edge of materials physics, despite being such an old material. And this relaxation behavior of glass and the flow of glass on long time scales, it's not just of interest for problems like determining whether or not cathedral glass flows. It's also critically important for many high-tech applications of glass. For example, these screens that you are looking at right now, these are made up of at least two pieces of very thin, highly engineered sheets of glass that have to be dimensionally stable during processing. And if the glass is flowing over time, that can lead to misalignment of the pixels. This is especially important for high resolution displays where the pixel sizes become smaller and smaller. You might be looking at this on a smartphone now. If you are, you're looking at this through a piece of most likely Gorilla Glass or some other chemically strengthened glass. This glass gets its strength through an ion exchange process, which installs stress at the surface of the glass. But if the glass is flowing, that stress is relaxing, and that compromises the strength of your cover glass. So this is a really important question for the dimensional stability of displays, for the strengthening of the cover glass on your phones. You are also using the internet right now by watching this video. All of this information is being sent at the speed of light through very thin strands of glass known as optical fiber. And the ability of these glass fibers to transmit this information is really governed by the Rayleigh scattering. And that is a function of how much the density is fluctuating within the glass, and that is controlled by the relaxation behavior of the glass too. So really everything that we're doing right now in transmitting this information over the internet, watching it on a display, that is all made possible by understanding and controlling the flow and the relaxation behavior of glass. So it's technologically very important. Now, one of the key concepts that we need to learn to understand this is the definitions of glass transition temperature and fragility. Now, there are multiple definitions for these properties, but the ones that we're going to use, and the person who originally proposed this concept of fragility, was Professor C. Austin Angell from Arizona State University. He published this very famous Angell plot where he took the viscosity versus temperature curves for many different types of glass-forming liquids and plotted them all on this master plot here, where you have the logarithm of viscosity on the y-axis, and then a normalized inverse temperature on the x-axis, where it's normalized by this glass transition temperature Tg. So 1 on this x-axis here corresponds to the glass transition temperature for each one of those different glass forming systems. And Angell defined the glass transition temperature to be the temperature at which the viscosity of the supercooled liquid is equal to 10 to the 12 Pascal seconds. He chose 10 to the 12 Pascal seconds because the viscous flow with this value of viscosity occurs on a time scale that is approximately equal to a typical experimental time scale for observing the system in a laboratory. So, in other words, if you have a liquid with a viscosity that is less than 10 to the 12 Pascal seconds, meaning that it's at higher temperatures, then it's flowing fast enough to observe the flow on a typical human timescale. But if you are at lower temperatures, which causes the viscosity to be higher than 10 to the 12 Pascal seconds, then that flow is so slow that you are kind of crossing over into more solid-like behavior. So this first definition here is the glass transition temperature, and that is defined as the temperature at which the viscosity of the liquid is 10 to the 12 Pascal seconds. The other key parameter is the fragility, and this is quantified by the fragility index M. And this fragility index is just the slope of this angel plot at the glass transition temperature. A steeper slope here means a higher fragility. That means that the viscosity is changing more rapidly with changes in temperature. And one of the nice things about the angel plot is that if you know these two quantities, if you know the glass transition temperature and you know the fragility index for a given composition, then that gives you a really good idea of the entire viscosity versus temperature curve, at least for the liquid and the supercooled liquid state. Now, a lot of progress has been made on both the theoretical and the experimental fronts since the original publication of the papers by Zanotto and by Zanotto and Gupta back in the late 90s. Back at that time, the state of the art for quantifying the viscosity temperature relationship was this Vogel-Fulcher-Tammany equation, which, as I mentioned, dates back to the 1920s. It's not a physically derived equation, and it has what's called a mathematical singularity, meaning that it actually predicts viscosity going to infinity at a finite temperature, which is unphysical. And the reason that this is important for our cathedral glass question is that we're interested in the flow of glass at very low temperatures, and the VFT equation gives highly inaccurate results in low temperatures, including this prediction of an infinite viscosity at a finite temperature. So one of the advances that have been made since then was the introduction of this Maega equation by these authors back in 2009. This equation gives a more accurate description of the shape of the viscosity versus temperature curves for the liquid state. And you can see here the VFT model is being shown in blue. And if you consider the same glass transition temperature and the same fragility index, the Maega equation is being shown in green, and the curvature is somewhat less. And the curvature is less because this only reaches infinite viscosity when the temperature goes to absolute zero, because it's only in the limit of absolute zero temperature that the kinetics are impossible. So viscous flow is only strictly impossible if there's a complete lack of thermal energy, and that only occurs in the limit of absolute zero temperature. One of the other models that have been proposed in between these two is this AM equation due to Avramov and Milchev. That is being shown here in red, and that has the least amount of curvature of the three models. In order to test these three models out and in terms of their ability to predict the low temperature viscosity, we put them to a test of several hundred different glass compositions, used each of the models to fit the high temperature viscosity data, and then extrapolate the models to predict how the low temperature viscosity would scale. Then we would compare those predictions to actual measurements of the low temperature viscosity, in this case at 10 to the 11 Pascal seconds. And what we found is that the VFT equation would systematically overpredict the low temperature viscosities, and it was over-predicting the temperature at that equivalent viscosity by about 12 Kelvin, which is quite a bit. And this is an error that would just get worse and worse the lower that you go in temperatures. Now, the Avramov-Milchev equation was actually under-predicting. So this was under-predicting the low temperature viscosity point by about 5.5 degrees. So it was doing better, but it had systematic error in the opposite direction. With the Maega equation, this was able to give the most accurate prediction. Actually, the prediction was within experimental error, so only about half a degree off on average. Now, the Maega equation, like the VFT equation, really just gives the viscosity temperature relationship for the equilibrium liquid or metastable equilibrium supercooled liquid. And that is what's being shown here in blue. As was noted by Prabhat Gupta in that second paper, what happens is when you get to viscosities at or a little bit above 10 to the 12 Pascal seconds, we have this falling out of equilibrium. Now, in that paper by Zanotto and Gupta, they had considered the theory at the time was kind of a sudden transition from equilibrium to this isostructural viscosity that has this Arrhenius scaling. Since then, a new equation had been developed, this MAP equation from these authors here shown at the bottom. And the MAP equation provides a more accurate description of this glass transition process, where it's not a sudden transition from the liquid to the glassy state, but rather a gradual transition. You can see how the curvature here is changing gradually as the supercooled liquid departs from the blue line. It goes through this curved region, through this glass transition region, and then gradually freezes into this straight line behavior where the scaling is Arrhenius. And only at that point is the viscosity strictly isostructural. Now, depending upon how fast or how slowly you cool the supercooled liquid, you can freeze in the structure of the glass at different points. And those points where you freeze in the glass structure can be given by the so-called fictive temperature, TF. If you were to cool the supercooled liquid very rapidly, you would fall out of equilibrium at a higher temperature. And this green curve here shows doing exactly that. So fast cooling here gives a higher fictive temperature. If you were to cool more slowly, the system has more time to stay in its metastable equilibrium, and it only falls out of equilibrium at lower temperatures, in this case at around about 720 degrees C. And what you can see is that the value of this fictive temperature has a pretty big impact on the viscosity of the glass. Just going between these two different curves here, if you just draw a vertical line through here, this would be comparing the viscosities of the same glass composition, the same temperature, the same chemistry, but just two different cooling paths. And if you have a faster cooling rate with a higher fictive temperature, that viscosity can be one, two, even more than two orders of magnitude lower compared to the viscosity of the slower cooling rate. The other thing you'll note is that the viscosity of the glass here is actually quite a bit lower than the viscosity of the liquid at the same temperature. And so the viscosity of the glass could actually be surprisingly low compared to what you might think intuitively. Now, this map model actually has two parts to it. I'm not going to go through this whole derivation here, but I'll just point out that there's two parts. This first part shows the isostructural contribution, and this shows the Arrhenius dependence with respect to temperature if you have a fixed fictive temperature. So this term here is what gives you the Arrhenius scaling of viscosity in the isostructural regime. The other term depends only on the fictive temperature TF and not on the temperature T. And this is what gives the thermal history dependence of the viscosity. So in going between the green curve and the red curve here, that is what's captured by that second term and the map equation. And then there are a few unknown parameters that have to be determined by most preferably by comparing to experimental data or by theoretical prediction. And the validation of this map equation has been done for a variety of different industrial glasses. These are two different display glasses from Corning Eagle XG glass and Jade glass. And what you can see is if you take a bar of these glasses and just hold them at a constant temperature. So on the left here, this is taking Eagle XG glass and holding it isothermally at either 600 degrees C, 650 degrees C, or 675 degrees C. Over time, this is as a function of time, the viscosity here on the y-axis is increasing over time. And the reason that it's increasing over time is that if you take the glass here and hold it at a constant temperature, over time it is continuously trying to relax towards the equilibrium liquid. And as it relaxes towards the equilibrium, it is moving upward vertically from either the green or the red curve here toward the blue curve. And as it moves upward, the viscosity is increasing. And this is a spontaneous process as the glass relaxes and it tries to reach something closer to a thermodynamic equilibrium. That involves the viscosity increasing and increasing on a logarithmic scale. So this is increasing by orders of magnitude. For example, here in this case, for an isothermal hold at 600 degrees C, the viscosity is starting out at 10 to the 13.5 or so, and then it is increasing all the way up to close to 10 to the 16 Pascal seconds over this time period of 8,000 seconds. If the isothermal holds are at higher temperatures, that increase of the viscosity happens more rapidly. Now, for a different glass composition here, according jade glass, you can see the same type of behavior. In each of these plots, the solid black lines show the experimental results, and then the dashed red lines are the model predictions from that map equation. So it provides a really good prediction of how the viscosity is evolving over time for different thermal histories and for different holds at different temperatures. Now, getting back to cathedral glass, one of the other things that was missing from that paper by Zanuda and Gupta is that they had used modern soda-lime silicate glass to as kind of a stand-in for the medieval cathedral glass because that's where the data had been collected and published in the literature. But we wanted to go back and use an actual cathedral glass composition. Rather than taking glass from a cathedral, we made our own. We got the recipe here for making colorless Westminster Abbey glass. This is the composition of Westminster Abbey glass. And you can see it's actually quite a bit different from modern soda-lime silicate glass in that it is lower in silica. It's quite high here in calcium, but it's really high and potassium. So the sodium here is a lot lower than modern soda lime glass, but the potassium is much higher. It also contains some phosphate in there and a bit of manganese. And so we made our own Westminster Abbey glass following this formula using the same raw materials that were used in medieval days. And we measured the viscosity. And what's shown up here is the Maega equation written in terms of Angel's parameters, the glass transition temperature Tg, the fragility index M, and the extrapolated infinite temperature viscosity A to infinity. My colleague Osgard made really careful measurements to get the glass transition temperature for Westminster Abbey glass, which he found to be 592.75 degrees Celsius, and the fragility index, which is 41. And so we've got the key parameters here that we need for the equilibrium liquid viscosity. The next step is to get the parameters that are needed for the non-equilibrium glassy state. These viscosity measurements are conducted by beam bending experiments where you put a beam of the glass in a 3-point bending configuration, hold it at different isothermal temperatures in separate experiments. These are isothermal holds at 522 degrees C, 552 degrees C, and 567 degrees C. Holding them over time, then the deflection is measured as a function of time. That deflection data is used to back out the viscosity here by this equation. And then that viscosity versus time and temperature data is used to deduce the parameters for the non-equilibrium viscosity model. And this shows an example of the log viscosity versus time. The noisy points here are the experimental data. They're kind of noisy because this involves taking a numerical derivative, and then the model fit using the map equation is shown by the red line. And the key thing is that The model parameters are the same at all temperatures and all thermal histories because the model parameters are a property of the glass itself. So, Oscar did some fairly heroic viscosity measurements here. He actually measured the viscosity. It was close to 10 to the 18 Pascal seconds, a direct measurement of viscosity, which took him weeks to do because of how slow the flow was. And the model predictions here are shown in red and in black. The black curve is the equilibrium viscosity of the liquid of Westminster Abbey glass. The glassy part, the non-equilibrium part, is shown by the red curve. You can see the departure from equilibrium around the viscosity of about 10 to the 12 Pascal seconds. And then as the glass is cooled, the viscosity continues to increase. The lowest temperature viscosity measurement taken by Oscar is this blue point shown here, and you can see very good agreement between the experimental measurement and the model prediction. And based on this, and then extrapolating this curve down to room temperature, the room temperature viscosity of Westminster Abbey glass was then found to be 3.8 times 10 to the 24 Pascal seconds. And so this is if we just put all that in the exponent, 10 to the 24.6 Pascal seconds. And this is rather surprising compared to what had been published previously by Gupta and Zanotto, using their modern soda-lime glass and the models and the experimental data that were available at the time. What they had predicted was a room temperature viscosity of 10 to the 41.3 Pascal seconds. And that extremely high viscosity was what gave the result that it would take 10 to the 23 years for the glass to flow. Keep in mind that was about 9 to 10 orders of magnitude lower or faster compared to the original estimate by Zanotto, which was assuming just the liquid state of the viscosity. So this was already about 9 to 10 orders of magnitude faster. And what we were finding is about another 16 orders of magnitude faster flow of our using real medieval glass, using our advanced characterization techniques and our advanced modeling techniques. So this more accurate estimate then of the cathedral glass viscosity is about 10 to the 24.6 Pascal seconds. So that is a much lower viscosity, which would indicate that the glass is flowing much faster than what had been previously thought. But the other part that was missing was actually doing some fluid flow calculations. So our colleague Olish Boratov did the fluid flow simulations using this viscosity. And in fact, considering a range of different fictive temperatures based on how, not knowing exactly how fast or how slowly that glass was cooled, and then calculated the surface velocity of that flow. And what he found was that the glass would exhibit about a nanometer's worth of flow over a billion years. So even though this viscosity was so much lower than what had been previously thought, it's still much too high to actually observe flow of cathedral glass windows. So do cathedral glasses flow? Yes, but not on timescales that are accessible to humans and not even on geological timescales on an observable length scale. So why is it then that many cathedral glass windows have thicker glass at the bottom compared to the top? This goes back to the medieval process for making flat glass. And in fact, flat glass wasn't very flat until more modern technologies were invented, like the Pilkington float process, which is the process by which all modern flat glass is made for architectural applications. It's this modern technology that gives us the uniform thickness that we enjoy today in our windows. But back then, and for many hundreds of years, the process for making these glasses was called the crown process. This involved taking a gob of glass, sticking it at the end of a rod here and spinning it, and then it would spin out into a disc. That disc of glass would be cut up into pieces that could be put into the stained glass window. And of course, the glass would be thicker in the middle compared to the outer parts. And so there would be thickness non-uniformity in the glass because of the way that it was being made. And then when the stained glass artisan would put it in place, it's only natural to put the thicker part in the bottom because that gives at least the appearance of greater stability rather than having the thicker part at the top. And so the cathedral glasses are not flowing on a time scale of hundreds of years. It would take longer than the age of the Earth to really have any observable flow. And the reason for this thickness non-uniformity is because of the process that was used back in medieval times. So to conclude, recently developed viscosity models and advanced measurement methods have enabled us to give a more accurate estimate of the viscosity of medieval glass at room temperature, even though those predictions are about 16 orders of magnitude lower compared to previous estimates. The viscosity is still too high to observe flow. So I hope you enjoyed this. If you'd like to know more, we published a paper on this topic in Journal of the American Ceramic Society. It's called Viscous Flow of Medieval Cathedral Glass. So you are welcome to look that up if you'd like to learn more. All right, thank you very much for watching, and I'll see you next time.